Okay, so today we are, you said, in for a very beautiful lecture. What we're going to do is look at a special class of surfaces. So just a reminder, we said in 3 dimensions you have 2 representations for surfaces that we commonly use. The one is a scalar function equals to 0. Okay, for example, for the sphere, it's simply, this is the scalar function x squared plus y squared plus z squared minus 1 is some function which we put to 0, which then describes the sphere. And we said that the normal vector is simply the gradient of f. Okay, then I said there's a second way of representing surfaces that I don't know how much you've used it so far, but what it is basically is you've to specify a vector that identifies each point on the surface. Okay, and because it's a surface, there are 2 degrees of freedom. So what that is basically, it's a map from 2 parameters to R3. And for example, what we have is the unit sphere over here. Your 2 parameters are the 2 angles. And then here we have specified simply the coordinates based on those 2 angles. So as I vary theta and phi, I can swipe out the whole of the 2 sphere. And I said if you have this representation, it's very easy to find the tangent space. It's simply partial derivatives of f will give you vectors that span the tangent space. So for example, over here, we have the normal spherical coordinates. Here we have e phi that always points in the sort of constant z, but sort of tangent to the circle. You draw it constant z, this green circle, and you have e theta that points tangent to the circle of constant phi, around like that. And you can see if you take s derivative with respect to theta, you simply get e theta, and you take s derivatives with respect to phi, you get a rescaled version of e phi. Okay, so our tangent vectors are related to the partial derivatives of the actual parameterization of the surface S. Sorry, the partial derivatives of the parameterization of the surface S. Okay, and as I also said, is this picture is just stuck for, at the moment, for flat space in 3 dimensions. I'm going to build everything up in curved space, what's coming, but it's just to start giving you a feel for what's possible. Okay, so now, okay, one important thing is, in this particular case, e theta and e phi are orthogonal. In other words, e theta dotted with e phi is 0. It need not necessarily be true. If you take these partial derivatives of your parameterized surfaces, you will get 2 vectors, but their dot product need not vanish. Okay, and then if you want to have an orthonormal basis, you've got to normalize those vectors and do basically work out and find a linear combination of them that are actually orthogonal. So now what I want to look at, it's kind of fun because it's such a simple example. It's a subset of surfaces in 3 dimensions. And it's a subset that's very easy to calculate with, that's why it's been so well studied. And it's also very easy to build. And it has a lot of applications. So it's just kind of a fun introduction. And it also, even if you go further and you make a subset of these, you get all the surfaces we worry about in origami. So it's a ruled surface, and some people also view it, call it a scroll, right? Like the ancient people that had those papyrus scrolls. It's those surfaces fit into this, this category. And so what the surface has is that on every point, there is a straight line that lies on the surface. So for example, look at this surface that you can make, that somebody made here very beautifully with, they basically drew 2 circles and then they joined the line at the top of the circle to the other circle. It's called a hyperboloid. Okay, so if you look at the surface, at every point, okay, you're going to have a straight line that goes through that point that lies entirely within the surface. Okay, so that property makes it very easy to write down a mathematical formula for the surface. Okay, couple of examples, a plane, right? Any flat sheet of paper, which I don't have because I've folded them all, But any flat sheet of paper, if this thing were flat, it's a ruled surface. Every place where you have a point, you have a straight line going through it that lies within the surface. Another example is a cylinder. So if I were to take this and I were to bend it into a cylinder, which it's not doing very nicely. Right, if I take my piece of paper and I bend it into a cylinder, at every point I'm going to have a line that is a rule that lies entirely within the surface. If I fold it into a cone, okay, the same thing is true. At every point of my cone, I'm going to be able to find a line that lies entirely with the surface. And this is another example. That's our hyperboloid. So now, with these surfaces, the easiest way of representing all of them is to actually use the parametric representation. So the parametric representation of a ruled surface or curve is simply a simplified version of what we looked at in the previous slide. You have a map from an interval to R3, okay, and you can basically make it up from a curve, like any curve, for example, the circle up here, okay, that maps from the interval to R3, and a non-zero vector, okay, so that at each point on the curve, you're going to have another non-zero vector, and we're going to call it R, that also maps from the interval to R3. So, for example, if you look at this 3D model, our curve is the circle up top here, and at every point, these yellow strings point in a certain direction. That direction that they point in is our vector R, that they call the directrix. It's basically the line along which this curve that makes up the surface is going to leave. Okay.
Tangent line.
It's not a tangent line. It can be a tangent line. Okay. Look here. So the tangent line to the curve would be in this plane. Okay. This thing is at an angle to the curve, and it's angled down in another direction. Okay. So it's simply any vector, okay, that you specify along the curve. So you have a curve that you have a parameter of, and then at every point on the curve, you specify a vector, okay, and that vector we call R, and then what we do, we also call it the directrix. It's basically the one that directs along the direction at which the line leaves the curve. And then we say, fine, we can express our ruled surface as follows. It's the parameterized surface, so it's a function of u and v. If v is 0, the curve lies on it. And then it is made up by traveling a distance v in the direction u. Okay, so for example, once again, for this hyperboloid that the model is of, is you start on the circle, that's where v is equals to 0, and then say v equals to 1, you basically travel a distance of 1 along every single one of these directions R of u. Okay, let's look at some more examples. So remember that spiral we did in the last lecture. You can take that spiral and you can say, fine, remember you had the spiral and then you had the normal direction that pointed away from the maximum curvature. You can say, fine, let's take the spiral and let us make R to be the negative of the normal vector for the spiral. So what we had is the spiral, remember that we had in the last lecture that I made the concycling circles of. And then I'm going to say, fine, this is my curve C, and everywhere along C, I'm going to make the normal vector of the curve my directrix. So there we go, or negative the normal. Remember the normal vector was pointing in towards the curvature, where the curvature is. So I'm going to make the negative of the normal vector. In other words, it points outwards from the curve. That's my directrix. And then I can make the surface that way. And the way I make the surface is I can travel a certain distance v in this direction and make the surface that way. So one little segment of the surface, I can simply say, okay, I start here, excuse me, I travel along this directrix and then I make the surface by joining that to the previous one. And then over here, I add the next part of the surface. I travel along this directrix with a certain distance v, and that's my next sort of bit of the curve, of the surface. And so I actually sweep out the surface by adding more and more bits where I simply are traveling along this normal vector to make my surface. And so if you ever want to design a spiral staircase, there we go. Okay, so this is an example of a generalized helix.
So in this case, I want to say we use the property in reverse. We use a straight line to build the surface rather than a straight line on the surface.
Yes, but it has both, right? The surface, ruled surfaces are given by the property that every point there's a straight line through it. So if you specify the straight line, you simply use it to sweep out the surface. Okay, and that will then ensure that at every point you have a straight line going through the surface. So in some sense, this is the abstract definition. It is entirely equivalent and included in this description. Okay, so there we go. We keep on making it. It's kind of cool to make these things. Okay, so we basically travel along, and I actually made it that the distance v as I go up gets smaller and smaller. Okay, so you travel along and you sweep out this helix like that. Okay, so you're going to play a little bit with the helix eventually, or some of the other examples, but this is basically an example of a ruled surface. Another example of the ruled surface that's actually slightly easier is the Mobius strip. I don't know if you've played with a Mobius strip. If you actually want, it's an example of a ruled surface. And to describe it, you're going to have two parameters that live between, or u is going to live between 0 and pi. Okay, and you're going to have a curve that's basically a circle, okay, except that you go around it twice or more rapidly, right? So this is basically a circle. If u goes to pi, if u goes from 0 to pi, this thing is basically swept up an entire circle. You go from 0 to 2 pi. And then, okay, so there's my circle. That's simply my curve. And then I'm going to specify my directrix, or the tangent at which I leave the curve with, as by the following formula. It's going to be cos of u times cos 2u, cos of u times sine 2u, sine of u. Okay? And if I go about and I plot that, I get something like this. Okay, so this is simply these vectors that at each point of the curve I go and I plot the vector, and then I can go about and once again construct my surface by traveling a certain distance along that vector called v, and in this case I'm going to travel the same distance minus v, and so my interval v is going to go from minus 0.3 to 0.3, and I'm going to then sweep out a surface that basically looks like this. Okay, so you can see as the directrix changes, your surface changes. It literally, in the case of the Mobius strip, does a twist over and joins back on itself. Okay, and there are many other nice properties of playing with the Mobius strip, but for our purposes, it's simply this description. Okay, so that's the basic quick introduction to ruled surfaces. What we're going to do when we actually look at the paper is we're going to look at a subset of ruled surfaces. And the reason for that is that you can't fit a page to this. So this is an example of a ruled surface, this hyperboloid. But there's absolutely no way you're actually going to fit a page to that. Right? There's no way you can fold this thing out of a flat piece of paper. And so there must be at least a restriction on the number of ruled surfaces we have that actually you can fold from paper. Okay. So this hyperboloid is also an example of what they call a doubly ruled surface. There's two ways of specifying the vector r. It's very unique in that sense. You can either specify to point along the yellow lines over here, or you can specify to point along the red lines, but there are two rulings is what they call it for this particular surface. Okay, but this thing you can never fold. So let's have a look at the concepts we need to actually decide which surface or which ruled surfaces you can fold. And before we do that, let's just simply look for the particular ruled surface. Let's make our tangent and our normal, right, of the tangent plane. So the tangent plane, remember, is simply at each point, if you were to put the best approximation of a flat plane to that surface is your tangent plane. So for our ruled surface, we have this parametric representation of the surface. Okay, we work out the partial derivatives. In other words, the SDU is simply C prime U plus V times R prime U, and the SDV is simply R of U. Okay, so this, I say, these two vectors then basically span my tangent space. Okay, so the one is useful, the SDV is just the rule direction, which makes sense, right? If you have a tangent, say, to the surface at this point, one of the directions in the tangent plane is just going to point along your directrix. And then the other vector is this the SDU, which is simply this guy. Okay, so what I say is these vectors span the tangent plane, and the normal to the surface can be computed by simply being orthogonal to these two vectors. So the normal to the surface is simply the cross product of the SDU cross the SDV. And so what I have now is that our normal is, I simply write this thing out, it's simply C prime U cross R times V times R prime U cross R. Okay, so that's just writing out the definition I did 2 slides back. So that's the normal vector. So one thing to note is our normal vector is always orthogonal to R. Okay, the reason being for that is that the normal vector of a cross product is always orthogonal to components of the cross product, and one of the elements in the cross product was R. Okay. Now let's do something else, okay? The fact that n dotted in with R is 0 does not mean, okay, so let's look at this particular curve. Let's look at one of these yellow curves, right? Along these yellow curves, at every point there's a vector R that points along it, and that vector remains constant for the entire yellow curve, okay? So now what you have, if you have a plane that's normal to this, you have another vector that makes the tangent plane. Okay? So along here, your normal vector, your R vector is constant along a yellow line, but your tangent plane is not, because the other vector changes. Okay? So along this particular curve, your normal vector points normal to the surface. And even though n dot R remains 0, it does not mean the normal vector remains constant. It can change. Okay. So what we're going to do now is look at the restriction of these surfaces so that the normal vector actually remains constant. Okay, so what we do is we say, let's pick one point on the curve, and we call it U0. Okay. And then the tangent planes along the line x equals to u0 comma v. Okay, so you're going to have, you have the surface that's a parameterized surface. Within the surface there's one line, like one of these yellow lines on my hyperboloid. Okay, it's a line that intersects the circle or the curve at a particular point, and then it simply has u0 constant all the way along the line. Okay, and I can describe the line, it's simply the distance you have gone along your R, your directrix, for that line. Okay, so now if along this line C prime cross R is a multiple of R prime cross R, okay, or equivalent, this is an equivalent expression. If that is true, okay, then the tangent plane doesn't change. Okay, why do I say that? Right? So you have your, or then the normal, yeah, both the normal and the tangent plane doesn't change. So how do you see this? Here's the curve that's basically, or the line that's leaving the curve. If C prime cross R is a multiple of R prime cross R, then the normal is equals to C prime cross R plus something that changes along the curve, okay, but R prime cross R is a multiple of this thing. So the direction of your normal remains the same. Do you see that one?
What is V again? V is the vector that points...
V is not a vector.
V is the scalar.
V is the scalar that tells you how far you have traveled along the curve. Okay, so if V is 0, then the normal to your plane is simply C prime cross R. Okay, as you travel along the curve, right, you've gone from this with V0 up here. As you travel along the curve, you've gone a certain distance. If at that point the normal vector simply didn't change its direction but simply rescaled itself, then you still have the same plane. Okay, so that condition is that C prime cross R is a multiple of R prime cross R. Then your normal vector doesn't change as you travel along the curve. Okay, and then you basically have one plane that you can fit to the whole thing, which is not possible for the hyperboloid. Okay, and this expression, this condition that C prime cross R is a multiple of R prime plus R, is equivalent of simply saying that this determinant, in other words, the cross product of these two is 0. Okay, so these two expressions are equivalent. And that then is the restriction we have on a developable surface. Okay, so a developable surface basically is a ruled surface, okay, that is developable into a plane. In other words, you can actually put a plane next to your ruled surface and then roll it out flat. If this determinant is 0, okay, so given a ruled surface, you can always work out what the derivative is of C, what the derivative is of R, and then calculate this determinant and put the conditions that it's 0, and then you are sure you have a developable surface. So you can basically check the condition that the surface is developable. And the reason you want to check that, for example, suppose you have a cone, right? What you can do with a cone is you can always roll it out flat so that it becomes a sheet of paper. So all surfaces that you can roll flat into a sheet of paper, 1 are ruled surfaces, and 2 have the additional condition on the curve's derivative, the ruling derivative, and the ruling direction itself, that their determinant is 0, that they basically lie in a plane, or they're a linear combination of each other.
So for our case, we are working with ruled surfaces, and we want the normal to be not to change, to be constant. So we take that property, but that property also means developable surfaces. So for that case, all ruled surfaces is developable surfaces.
No. All ruled surfaces have this expression.
Yeah.
A subset of ruled surfaces, in addition to this expression, have this property.
Yeah, but aren't we going to work with that?
All
of the ones that we are going to look at.
All of the ones you're going to look at if you do origami or paper folding,
yeah,
right, have the property that they're developable. So the developable surface are a subset of all ruled surfaces, and they're the subset that satisfy this.
Yeah.
Okay? And the developable surfaces you can always take, regardless of what you are, and you can flatten them out into a sheet of paper. Okay? And so if you add this restriction, all the only surfaces you get is a cone, a cylinder, and a surface formed by tangents of a space curve. Okay, so a cone and a cylinder, and it's not just the cone, you can like cut a bit of a cone and you can make it, or a cylinder is not just a round cylinder, you basically can take any curve and you can make your paper make like a sine wave as well. That's a valid cylinder. And the surface formed by tangent of the curve is what you wanted to do right at the start. So suppose I have a curve and I have a whole bunch of vectors that are its tangent. That will make me a developable surface as well.
Like the staircase?
No, the staircase is not a developable surface necessarily, because there it's the normal.
The normal changes.
The normal changes. If I were to take that thing like that, then at each point I sweep out tangent, I'll also get something that looks slightly like a staircase, but it won't be that curve.
Yeah.
And that is also developable. Okay. Okay, so a feature that we're going to get back to is that a developable surface has zero Gaussian curvature. And I'm just going to tell you what it means. But zero Gaussian curvature is basically the curvature within the surface itself. It basically means that a rule surface is intrinsically flat. Okay, in other words, if you were to live only in the surface, there would be no way of finding out that it was a surface different from a flat plane.
Okay, so that's for developable.
For developable surface, it's not true for all ruled surfaces. Sorry, yeah. Okay, so developable surface, and that condition you can prove is entirely equivalent to this thing as well. Okay, we'll do that later when we've actually defined what this is. Okay, but all that this thing means is if you live if you're an ant walking on a developable surface, a very tiny ant, you cannot tell that you're not walking on a sheet of paper. Okay, and now the applications of this. Yes.
Sorry, can I ask there? So
please.
If you live on a sheet of paper that's folded into a cylinder, then you can cross over it.
Yes, but locally. Sorry.
Okay,
locally, you could. So you can imagine the sheet of paper you would just keep walking, and you would not be able to know when, in fact, you had crossed over it as well. But yeah, so there's no physics experiment that you'll do in your little lab that will be able to tell you that the surface is curved, the sheet of paper is curved or not, because it isn't curved. On the other hand, if you are working on the sphere, you can actually do a little baby experiment close in your lab and actually measure the curvature. Okay, and that's
why we are in 3D, because we can prove we have a curvature.
No, you can live, The Earth is a two-dimensional surface.
Yeah.
Okay, and it's not flat. And it's got nothing to do with 3D. You can stay on the two-dimensional surface, and you can go a little bit in certain directions and do things with vectors. And you can prove that you're not on a flat surface, that it actually has an intrinsic curvature to it.
But it's 2D.
It's a 2D surface. This is just 2D surface. And so there's a difference between properties that lie within the surface itself and the way that the surface is put into a high dimensional space. Like, so for example, the sheet of paper, if you were to live just on the sheet of paper, whether the sheet of paper is doing that or whether you've curved it into a cylinder, it makes no difference for the person just walking on the sheet of paper. It makes a difference for the person looking from outside, but not for somebody in the sheet of paper. So if you think of us living in 3 dimensions, right, we can try and measure whether it's curved or not within the 3 dimensions, but we can't see anything outside. Okay, there are things we can know about our space just within the space itself, and there are things that we can know about it as in how it's put into a higher dimensional space. Okay, and so the Gaussian curvature is basically the curvature that's right inside the sort of intrinsic to the surface. And there are other curvatures that tell you how the surface is put into 3-dimensional space. And so, for example, if you were to look at this flat surface with a circle drawn on it, okay, so the circle is a 1-dimensional thing. It has curvature itself. It has a curvature that's dependent on the fact that it's simply drawn on a flat plane. Okay, and that's going to remain unchanged in the flat plane. But now if I take the surface and I bend it into 3 dimensions, right, I'm still going to have the same line drawn and the same curvature in the flat plane, but from outside it's going to look a lot more curved because a component of my curvature is now coming from the line in the curve, in the plane, and another component is coming from the way I've put it into 3 dimensions. And what a lot of the origami or the curved fold origami does, it separates out those 2 properties. And that's what we're also going to start separating out for manifolds in general later on. Okay, so application, computer-aided design, a lot of the computer graphics that we have are working with developable surfaces. Like a lot of the, simply like the animations and stuff, describe them as a whole bunch of developable surface stitched together. And the reason for that is it's very easy to store colors and pigments, right? You know, so for example, what you do when you have a model in 3 dimensions and you want to put a color patterning on the surface is you basically wrap it. You basically find a map from its surface onto a flat sheet of paper so that you then can go about editing the design on the flat sheet of paper and then you just put it back around the model. Okay, so that's why this flat surface thing is used a lot, because it's very easy to represent compactly the texture on the flat sheet of paper, and then you just keep the map of what puts it onto the 3-dimensional surface. Okay, it's also very easy to keep this type of information for the surface to describe it. Okay, origami, folding the stuff, whether it's pieces of paper and sheets of metal. And so when people start manufacturing stuff from flat sheets of paper or flat sheets of metal, there are a lot of new architectural designs that actually make use of this mathematics. So from a geometry perspective, it's quite simple geometry, but the applications of understanding it are quite profound. So it's kind of a nice introduction to start with. Okay, so what this basically now leaves the foundation of, like the last lecture or 2, that I'm just going to derive the basic formulas that actually describe how you relate the curve in the flat space to the curve in the 3-dimensional space. So when we do origami, what we have is we study, especially in what I'm interested in and what Petrus might also take a look at, is how the creases actually influence what structures you can fold. Okay. So, for example, here's my flat piece of paper. I draw my circle on it, okay, and I then fold it along this crease. And there are certain shapes that the crease can take up that's actually designed, that comes directly from the curve I've made on top of it, okay? And you'll notice that there's an angle between the one sheet of paper and the other sheet of paper that varies along the fold. And so what we want to do is understand how those angles work, because we want to do structural things with it. Okay, so look also when I fold this thing only wants to go into a cylinder. All right, it can't do anything else. And that then influences what happens on the outside here, and here on the outside it's behaving like a cone. Okay, so we're going to start studying that interaction simply by using what we know about curves and developable surfaces to try and derive the results. And so I'm just going to put up the framework, and then I'm going to start deriving it tomorrow, I guess, and looking at a few examples. In fact, the reason people are interested, maybe I can just give a bit more introduction, is, for example, this thing. All this is a series of circular things that have been curved, but it's got some very nice dynamical properties that people don't fully understand. So this is an open problem. Basically, if you have concentric folds that go in, out, in, out, in, out, what it behaves like. And people actually are starting to build things out of this, because it's a very nice way of getting structure simply from a flat sheet of paper. So there's a rigidity to it as well. And the other one is the flasher example that I showed you. So there's a lot of cool things you can do with it. But to design cool things, you actually need a control of what's happening. So I'm going to set up the problem and then analyze it a little bit more tomorrow. Okay. So the basic problem with origami, and this comes from a paper by Domain. Domain is a professor at MIT that has been doing origami his whole life long. He's basically got the heritage from Hofmann. And I don't know if you know who Hofmann is. He's a computer scientist that most of the encoding, in other words, if you have an image, how do you store it compactly? And how do you like throw away all the excess information? If you were to store it pixel by pixel, it would be huge. But how do you sort of throw away all the excess information and store like the content as compactly as possible? And he's very, very famous for his algorithm that they call Huffman coding. If you do image processing, you'll come across that. So a lot of people know him for that. His hobby was origami. So he's got this most beautiful house that people went in after he died, where he's made all these structures. So a lot of these things actually come from his house. And he played with curved folds. He was one of the few people that played with curved folds and actually understood them. And in fact, he basically did the foundation for what this guy went on and did. And he made these beautiful constructions, and we still fully don't know the mathematics behind the constructions. So he had a little bit of the math. He used rule surfaces for his computer science sort of demonstrations and stuff. And in fact, he was one of the first guys to say, okay, if we represent like surfaces in computer science that are curved in terms of rule surfaces, we can actually represent them quite compactly. So that's where his interest came from. But he made these beautiful constructions that we still don't fully understand how he got to make them. So he played. You know, there's sort of this difference between dry mathematics and vectors and art. And the two actually, in this case, go together, where you have the artists simply trying things and getting unusual structures, and the mathematicians go back afterwards and study them. And in fact, what this guy is doing is he's basically going back into all the things that Huffman had in his house, and he's trying to describe them mathematically. Okay. So the basic structure is you have what we call the pattern curve, which in this case is simply the curve you've drawn on the two-dimensional surface, which is a circle. Okay. And for our purposes, it's stuck in 2 dimensions. It's only dependent on what's drawn on the surface. And I'm going to call it small c. And then you have the 3-dimensional space curve. Okay. And that is the curve, for example, here the small c is just the flat circle. When I bend the curve, when I bend the paper, then you get this 3-dimensional curve out here. That's the big C, okay, which has then three-dimensional components. Okay, and that's what I call the space curve. And both of those have all the properties I've discussed. Like the small curve just has the curvature in 2-dimensional space, and the big curve has curvature and torsion in 3-dimensional space. And we want to know, if you draw the small curve, how does it restrict the big curves that you can possibly draw? And as I said, it is not completely solved, right? There's certain things that I'm basically going to give you everything we know about them, and then Petrus is going to go on and tell us more. And we're going to go on to the generalized GR. Okay, another thing that's convenient is, or that we use, that I'm going to use at least with the derivation, is I'm going to assume these curves are parameterized with the arc length. So that's not always possible. In fact, when I did the flasher, or while I'm doing this flasher design where you have this flat thing that you basically fold up in a very particular way to pack it into the satellite and then go and you deploy it, right, like that. When I started applying the stuff to this flasher design, it's very hard to get the arc length parameterization. It's one of the problems. And you'll see, I'm going to give you a problem set, maybe hopefully out today, that you can actually try just some of the problems yourself. And you'll see that it's actually not so easy to get this thing explicitly, but you can work with it without actually having the explicit parameterization in the arc length parameter. Okay, so we have the arc length parameter. Then we have our tangent curve, which is defined exactly as what we've been doing it. For the 3-dimensional, for the space curve, it's simply d big C ds. For the small curve, it is d little c ds, but that's what it is. Another important feature is if you use the arc length parameter, whether you have the curve still folded flat, like this little cs, the distance you travel along it is the same, whether it's flat or whether it is curved up, right? You still going to travel from, say, from here to here, that distance is not going to be different, whether you're curved up or whether you're flat. Okay, so the arc length parameter for these two curves are the same.
Does that basically come from the property that you have a straight line surface, a root surface?
That, I've not yet said anything about the surface. Okay, that comes from the property that this surface doesn't stretch. We're assuming that the piece of paper doesn't stretch. And so what you're going to basically imagine is you have a piece of string that you put along this curve, and if you then take the paper and you stick it to the paper, if you take the paper and you bend it up, the curve's length is still going to be the same. So the fact that the arc length parameter of the two curves are the same is an assumption about the fact that our paper doesn't distort and it doesn't stretch. Okay, then we're going to define the curvature big K of the big curve, okay, to be dt ds, and kappa I'm going to keep as the curvature for the small curve. Okay, so that's just my notation. I'm going to have a little kappa, which is associated with a small curve's curvature, and a big K, which is associated with a big curve's curvature. Okay, and then we go on and we make our normal vector to be dt ds ds, and that's 1 over big Ks, and this is the normal vector to the big curve, to the three-dimensional curve. Okay, and so here I've actually, the three-dimensional curve here is the red one. Here's my tangent vector that points along it, the big T. Okay, and here's my normal vector, always pointing towards the midpoint of what the curve curves around, right? Remember those oscillating circles, it's pointing towards the center of the oscillating circle. And then from that, the tangent and the normal vector, I'm going to get this other vector that's normal to both of them and at 90 degrees. So I have my binormal that's over there. Okay, so far all this stuff is dependent just on this red curve. Okay, and then what we're going to do next time, and I'm actually going to stop here before I get into it too deeply and we go over time, is on both sides of this curve, I'm going to have developable surfaces. Okay, and those are going to be my sheets of paper, and then it's going to be studying the relationship between these three vectors that are associated just with a curve, okay, and the planes that are making up our surface, and seeing what's possible, because there are restrictions on, because you have a developable surfaces, you have a certain relationship between the plane and the curve and the directrix, and that actually chooses what possible curves you can make. Okay, and we're actually going to make those interactions explicit. And this wasn't done very recently. This isn't old stuff. It's actually interesting that developable surface paper only happened last century, 1900s, if you look at the date on that paper. And before that, people just didn't study it. And it's got so many applications for engineering flat sheets of steel that it's kind of amazing that it took so long to understand it. It's not trivial in the sense that it's finicky, but it's pretty straightforward. And once we've done it, you'll understand why we want a more general framework to actually work with surfaces. But it's just kind of cool intermediate result that you can immediately see the application of before we start doing the manifold thing. So thank you. So I'll see you tomorrow, and then we can do more on the surfaces themselves.